Okay, let's try a little thought experiment. Just for a second, imagine your world with no power, no heat in the winter, no way to cook, no way to keep your food fresh in the fridge, no computers, no TV, not even a way to make a phone call in an emergency. It's kind of crazy how much we depend on this invisible force we call electricity. So, how does it actually work? And how on earth did we learn to harness it? Well, in this explainer, we're going to dive in and demystify that very force. We're going to trace its journey all the way from a spark of curiosity to the global grid that we all rely on. And we'll explore the huge challenges we're facing right now in powering our world. All right, first things first. Let's get grounded in the basics. How do we even make electricity? Turns out it all starts with one simple, powerful rule. In physics, electricity isn't just one single thing. It's really about two things, electrical energy and the movement of electric charge. So when we say the power went out, what we really mean is that the flow of that electrical energy has been cut off. And this is absolutely crucial. We don't create electricity out of thin air. Every single power plant on this planet operates on this one fundamental law. They're all just giant energy converters, transforming one type of energy into another. And here you can see that very idea in action, just on a massive scale. A hydroelectric dam, like the one you see here, takes the raw kinetic energy of moving water and transforms it. A coal plant does the exact same thing, but with the thermal energy from burning fuel. The source energy is totally different, but the principle? It's identical. It's all about transformation. But, before we could even dream of building these massive power plants, we first had to figure out what electricity even was. And that journey is a pretty amazing story of scientific discovery, starting with a very, very famous experiment. So in 1752, Benjamin Franklin flies a kite in a thunderstorm. Now, he was way too smart to let lightning actually strike the kite. That would have been the end of him. Instead, a nearby strike charged up the key that was tied to the string. When he brought his knuckle close to it, he felt a shock, and that was it. He had proved that the mysterious, terrifying force in the clouds was the exact same thing they were experimenting with on the ground. And what's so cool about this is how completely obsessed these early pioneers were. Franklin himself wrote that he'd never been so engrossed in any study in his entire life. You can just feel the excitement and that sense of wonder in his words. But here's the thing. In that passionate quest to figure out this invisible force, Franklin and his colleagues, they made an assumption. Now, it was a perfectly logical guess at the time, but it turned out to be wrong. And the wild part is, we still use his wrong idea in engineering to this day. So here's how it breaks down. Franklin pictured electricity as a kind of fluid. He figured an excess of it must be positive, so he assumed it flowed from positive to negative. We call that conventional current. It wasn't until 150 years later that scientists actually discovered the electron and realized that the charge in a wire is actually carried by negative particles moving from negative to positive. That's electron flow. So why do we still use the old way? Honestly, because by the time we figured it out, the old convention was already so baked into everything. Okay, so now we have a model, two actually, for how this stuff flows. What's next? Well, you need a set of rules, right? You need a way to predict and control how it's going to behave. And that's where this guy comes in, Gustav Kirchhoff. Way back in 1845, decades before anyone even knew what an electron was, he laid out the fundamental rules of the road for all electric circuits. These are laws that engineers still use every single day to design everything from our power grids to the phone in your hand. So Kirchhoff gave us two key laws for two different kinds of circuits. In a series circuit, there's only one path. The voltage gets divided up, but the current stays the same everywhere. Think about old holiday lights, right? If one bulb burns out, the whole string goes dark because that single path is broken. But in a parallel circuit, there are multiple paths. The voltage is the same on every path, but the current gets split up. That's your kitchen. When one light burns out, the others stay on because the electricity has other paths to take. Okay, to really get this, let's try an analogy. Imagine the electric current is just a flow of people trying to get into an amusement park. And resistors, those things in a circuit that limit the current, are like the turnstiles at the entrance. Now, if you add resistors in series, it's just like making everyone go through multiple turnstiles one after the other. It's a huge bottleneck. The overall resistance goes way, way up, and the flow of people, the current, slows to a trickle. But if you add resistors in parallel, it's like opening up a whole bunch of new gates side by side. Even though each gate has a turnstile, you've created more pathways, so the total resistance actually goes down, and the overall flow of people, or current, goes up.
And it was by applying these very rules that we were able to go from tiny circuits in a laboratory to the massive electrical grids that connect our entire world.
Which, you guessed it, brings us right back to these guys. Whether it's a dam or a coal plant, the goal is exactly the same. Apply the laws of physics to transform incredible amounts of energy, and then use the rules of circuits to deliver it, reliably, right to your home. But, and this is a big but, the choices we make about how we generate all this power, they have real consequences. And that leads us to the biggest challenge of our time.
Let's look at coal. For a long time, it's been a go-to fuel because, well, there's a lot of it and it's pretty cheap. The problem, as we all know, is that burning it releases pollutants like sulfur dioxide, which causes acid rain, and just massive amounts of carbon dioxide, which is a major driver of global warming.
So, in response, engineers have been working on what are often called clean coal technologies. Things like scrubbers, which can remove the stuff that causes acid rain, coal gasification can make the whole burning process more efficient, and then there's carbon capture, which is this big idea to literally grab the CO2 emissions before they hit the atmosphere and then store them, usually deep underground. But at the end of the day, even with all these advances, the biggest hurdle is still the staggering amount of carbon dioxide. Figuring out how to stop it from getting into the atmosphere from all these coal plants at a global scale is still the single biggest engineering problem we have yet to solve. I mean, think about the journey. We went from flying a kite in a storm to building our entire modern world on this invisible force. We cracked its code and we wrote the rules. The question for us now is, what new rules and what new discoveries will it take to power our next chapter, not just powerfully, but sustainably?